Hello everyone. Today we are going to solve the differential equations using Laplace transformation. Before we solve differential equations using Laplace transformation, you must understand the elementary results of Laplace and the properties of Laplace, okay, and also the inverse Laplace transformation, because to solve differential equations using Laplace transformation we need to know both Laplace and its inverse transformation. And so if you are given any differential equation, we can apply this transformation to solve and find the particular solutions. So to solve a differential equation, the method is a three-step procedure. And say you are given a differential equation where variable is y function of t. So that means I am saying that the dependent variable in the differential equation is y and independent variable is t. Okay, so in the previous lecture we said we used functions ft, so that's why I'm specifically mentioning here that we are now using in this lecture symbol as y of t. Okay, so differential equations of first order, second order, third order, and so on, where the derivatives are dy by dt, d2y by dt square, and so on. Okay, so t is the independent variable and y is the dependent variable. Okay, so if you are given a differential equation with the initial conditions or boundary conditions, okay, then we can solve the differential equation using these simple three steps. Okay, and the first step is that you take the Laplace transformation on both sides of the differential equation. So whatever differential equation is there, you take Laplace transform on both sides of that equation. Okay, so what does Laplace transform do? It converts the differential equation into an algebraic equation, and the variable yt is transformed into a variable ys. So if you remember previous lecture when we said ft is the function, then the Laplace of ft we said is f of s. Okay, so similarly the Laplace of yt we are denoting by a symbol y of s. So Laplace of yt is y of s. Okay, and then whatever initial conditions are given to you, you can use those initial conditions after this first step. Okay, so why exactly I'm saying initial conditions here is because in the differential equation there are derivatives. Okay, and if you remember the property of Laplace transformation, that the Laplace transformation of derivative of a function, then you will find that it is equal to s power n ys times sorry, minus s power n minus 1 y0 minus so on y dash 0 minus y second derivative 0 and so on. Okay, so y values at t0, y dash derivative value at t0 and so on, these are required in the property of derivative Laplace of derivative of function. Okay, so your first step is very simple, that you take the Laplace transform of the differential equation on both sides, and then use whatever initial conditions are available to you. Okay, use them. The second step is that you have a algebraic equation in ys, so you solve this algebraic equation and calculate this unknown ys. Okay, so solve the algebraic equation for the unknown variable ys. Okay, right, so differential equation is transformed into polynomial equation, so from here you calculate this ys. Okay, and once you have ys, then your final step is just to take a inverse transform. Okay, because the Laplace of yt is ys, so inverse Laplace of ys will be yt. Okay, so take the inverse Laplace transform on both sides after step 2, and this will give the required solution of the original differential equation with variable yt. Okay, so steps are very simple. You take Laplace on both sides of differential equation, use the conditions. Okay, calculate the unknown variable ys, and then take inverse Laplace transformation. That will give the solution to the original differential equation. Okay, so I'm writing it again that we are going to use this notation in this particular lecture, that Laplace of yt is ys. So I'm using y as the dependent variable and t as the independent variable, and the transformed variable for t is s. Okay. So I'm going to take few examples here to show you how to use Laplace transformation to solve differential equations, and this is the first example that solve the differential equation using Laplace. And the differential equation is a homogeneous, right hand side is 0, it's a third order, okay, third derivative is there, first degree, okay, and with constant coefficients, okay, so coefficients of derivative and y term are constants, okay, and given conditions, so there are three conditions, okay, with the third order differential equation require three conditions. So the condition at of y at t0 is 0, the y dash at t0 is 0, and y second derivative at t0 is 6, okay. So the method is very simple, okay. Method says that you take Laplace on both sides of this equation, then use these conditions, calculate ys, and then take inverse Laplace, okay. So we'll follow this procedure for solving any differential equation, okay. So our first step is that we take Laplace on both sides of this differential equation, okay. So Laplace on left hand side and Laplace on right hand side. On the left hand side it is Laplace of sum of functions, so we can use linearity to separate them, and on the right hand side Laplace of 0 is 0, okay. So and so by linearity we have separated the left hand side, and if you remember the property, then Laplace of first derivative dy by dt is s y s minus y0. Similarly, Laplace of second derivative of y with t will be s square ys minus sy0 minus y dash 0, where dash means derivative, okay. And Laplace of third derivative is s cube ys minus s square y0 minus sy dash 0 minus y second derivative 0, okay. So we just substitute all these here, okay, on the left hand side, and Laplace of y we are saying is ys, so this ys here is nothing but Laplace of yt, okay. So substitute all these results here, okay, so that's our first step, okay. So third derivative Laplace is this up to here, okay, then plus 2 times Laplace of first derivative, second derivative, minus, okay, so there is a minus here, and Laplace of first derivative, so that's sys minus y0, and minus 2 Laplace of y is ys, equal to right hand side is 0, okay. So and then in the first step, once you take Laplace, it says that you substitute whatever initial conditions are given, so put y0 is 0, y first derivative 0 is 0, and second derivative at 0 is 6, okay. So use all conditions, okay. So this y0 is 0, first derivative is 0, so these two terms are 0, this will become minus of 6, so that's minus 6, y0 and first derivative are 0, so these two terms are 0, and y0 is 0, so this term is also 0, and rest of the terms are of ys, we can combine them, so ys this term, second term, third term, and fourth term, these four terms we combine to write the first function, okay. So this was step 1, okay. And interestingly, because this differential equation is with the constant coefficient, so you see what is the coefficient of ys here, s cube plus 2s square minus s minus 2, okay. If you look it here, it is like s cube plus 2s square minus s minus 2, okay. So you can immediately, if they are constant coefficient, you can immediately recognize this coefficient of ys, okay. And this part comes from the initial conditions, okay. And now the second step, okay, second step says that once you have the algebraic equation, then you solve this to calculate ys. So ys is easy to calculate, take the 6 to other side and divide with this, okay. So ys is 6 over s cube plus 2s square minus s minus 2, okay. So that's step 2. Then finally third step is that you take the inverse Laplace transformation on both sides of this, okay. And on the right hand side we have a denominator of polynomial of third power. So we did the method of partial fraction in the last lecture, so we're going to utilize that. So resolve the denominator into linear or quadratic factors, use partial fraction, and then we take Laplace inverse on both sides. Okay, so right hand side function denominator we can write as a product of linear factor s minus 1, s plus 1, and s plus 2, and then because each factor is linear of power 1, so we can use partial fraction to write it as a constant over s minus 1 first vector plus another constant over s plus 1 and plus third constant over s plus 2, and then we can calculate these constant by solving left and right hand side together. Okay, so I'm leaving this because we already discussed this in the last lecture. So once you have ys in this form, then the third step is that you take Laplace inverse on both sides of the different this equation. So taking Laplace inverse on both sides, so Laplace inverse of ys equal to Laplace inverse of this right hand side. Okay, and Laplace inverse of ys is yt. Okay, because Laplace of yt we said is ys, so its inverse Laplace will be yt back. And on the right hand side we can use linearity, so Laplace inverse of sum will be sum of Laplace inverse. Okay, so we can separate them using the linearity property, so Laplace inverse of first plus Laplace inverse of second plus Laplace inverse of third. Okay, and so we know the property that Laplace inverse of 1 over s minus a is e power at. Okay, so this is property. Okay, so we can utilize it here. Okay, because all functions here are of this form with different a constant. Okay, so this Laplace inverse will be e power t, the second will give e power minus t, and third will give e power minus 2t. Okay, so yt is equal to this function, and this is the solution of our first differential equation. Okay, so this is how you solve the differential equation. You take the Laplace on both sides. Okay, substitute the conditions, calculate ys function, and then take inverse Laplace transform. Okay, so now I take one more example. Okay, say solve the differential equation using Laplace again. Now it's a second order differential equation with constant coefficient, but it is non-homogeneous. Right hand side is non-zero now, and there are two conditions because the second order differential equation, both conditions are on t0. Okay, the y at t0 is 2 and derivative y at t0 is minus 1. So steps are still same. Okay, take Laplace on both sides of the differential equation. Okay, so that's first step. So Laplace on left hand side equal to Laplace on right hand side, and we know Laplace of e power t, it is 1 over s minus 1, and on the left hand side use linearity, separate the write it as Laplace of first plus Laplace of second term plus Laplace of third term. Okay, and then Laplace of derivative property we know, so okay, apply that property. Okay, so Laplace of second derivative is this, Laplace of first derivative is this. Okay, so substitute it here. So Laplace of second derivative is s square ys minus sy0 minus y dash 0 up to here. Okay, three terms, minus 2 times Laplace of first derivative, which is sys minus y0, and plus Laplace of y is ys, and on the right hand side it is 1 over s minus 1. Okay, then substitute the condition, y0 is 2. Okay, so put y0 is 2 here and here. Okay, and y dash 0 is minus 1, so put y dash 0 as minus 1. Okay, so use the given conditions. Okay, and combine the terms of ys, so s square ys minus 2 sys plus ys, so that will give this s square minus 2s plus 1 time ys. This will be obtained with the conditions, and on the right hand side is this. So again, if you, this is a differential equation is again with the constant coefficient, so if you compare the coefficient of ys here, it is s square minus 2s plus 1, which you can see from here also, s square minus 2s plus 1. Okay, so the next step is, we know next step is we have to solve this to calculate y's. Okay, so take this quantity minus 2s plus 5 to other side, and then divide with this s square minus 2s plus 1 to calculate y's. Okay, so we can calculate ys so as 1 over this quantity plus 2s minus 5 over this quantity. Okay, right, so here this s square minus 2s plus 1 is nothing but s minus 1 whole square, so this denominator becomes s minus 1 whole cube, and this denominator here is s minus 1 whole square. Okay, so we can write ys as this, and if I rewrite this numerator as 2 times s minus 1 minus 3, then I can cancel out s minus 1 and rewrite this second term as sum of these two terms. Okay, so once I have ys written in this form, then we have to use the third step, that is take the inverse Laplace transformation. So taking inverse on both sides, so Laplace inverse of ys and equal to Laplace inverse of this sum. Left hand side is yt and right hand side we have to use linearity. Okay, so yt equals to Laplace inverse of first plus Laplace inverse of second plus Laplace inverse of third. Okay, so in this third it is 1 over s minus 1, its Laplace inverse is e power t. Okay, but here the power is square and cube, so we have to use first shift theorem. Okay, so if you remember first shift theorem, that it's a Laplace inverse of 1 over s minus a power k is e power a t Laplace inverse of 1 by sk. Okay, we use first shift here. Okay, multiplication of by exponential. So and then Laplace inverse of 1 by s power k we know. Okay, so we can easily do this. So Laplace inverse of this is e power t, and Laplace inverse of 1 over s minus 1 square. So again e power t, and 1 by s square, its Laplace inverse is t. Okay, and here it is e power t. Okay, so Laplace inverse of this is easy to calculate, and so we have the solution to the differential equation as yt is equal to half t square minus 3t plus 2 times e power t. Okay, so this was example 2. Now I take a third example. Say solve the differential equation using Laplace transformation. Again, it's a non-homogeneous differential equation of second order, but now the coefficients are not constant, but they are variable coefficients. Okay, so coefficient of second derivative is t, and also the coefficient of y is t. Okay, and the only one condition is given, which is y0 is equal to 1. Okay, so let us solve this again by the same method. Okay, so first step is to take the Laplace transformation on both sides of differential equation. Okay, so Laplace on left hand side equals Laplace on right hand side. Laplace of cos t we know is s over s square plus 1, and on the left hand side use linearity. Okay, uh, Laplace of derivatives we know. Okay, for the last two examples we said this, and then we use the property that Laplace of if y is known ys, then Laplace of multiplying with t means minus d derivative with respect to s of y's. Okay, so we use the property of multiplying with t here. Okay, so Laplace of second derivative multiplied with t, so multiplication with t means minus first derivative with s of whatever is the Laplace of second derivative, and Laplace of second derivative is this s square ys minus s y0 minus y dash 0 plus 2 times Laplace of first derivative, and Laplace of first derivative is s ys minus y0, so plus 2 times s ys minus y0 plus Laplace of t times y, so again multiplication by t is here, so minus first derivative with this of Laplace of y, which is ys, and on the right hand side is s over s square plus 1. So now use the conditions. Condition is y0 is 1, so put y0 is equal to 1 here. Okay, the y dash 0 value is not given, and in fact in this particular problem it is not required, because whatever is the value we have to differentiate with this, and so this derivative with s of this constant will be 0, so this term will get eliminated once we do the derivative here. Okay, so put y0 value as 1. Okay, use the derivative. Okay, and then combine the terms. Okay, so derivative of s square ys, so you have to use product rule, so s square times derivative of ys plus 2s ys, and derivative of sy0, so that's y0, and y0 value is 1, so that's minus 1. Okay, and plus 2s ys minus 2, because y0 is 1, and minus derivative ys equal to s over s square plus 1 this term. Okay, so you can see that minus 2sys and plus 2sys, these two terms will cancel out, the second term here and the first term here, and rest we can rewrite to calculate, combine the terms of dy by ds, these two terms, and take the constants to other side, and then divide the coefficient and calculate dy by ds is equal to this. Okay, So now we have calculated, like we said in the second step, calculate ys. So here it is in the form derivative, so calculate derivative. Okay. And now use the third step. Okay, third step is take inverse Laplace transform. Okay, so because we know that Laplace of tft is minus derivative fs, so Laplace inverse of derivative we know is minus tft, so it is minus t by t if we take Laplace inverse of left hand side, and also we take the Laplace inverse of right hand side by using properties. Okay, so now we have this function, take Laplace inverse on both sides. Okay, so Laplace inverse of derivative of ys is equal to Laplace inverse of this sum. Use linearity on the right side. Okay, and Laplace inverse of first derivative ys is, we know by property, it is minus t by t. Okay, because the Laplace inverse of ys is by t. Okay, and on the right hand side we use linearity to separate them, and I've written this in specific form, s over s square plus 1 times 1 over s square plus 1. Okay, now you have two options here, either we can use partial fraction type of thing, or we can use convolution if we know the product. Okay, individual Laplace inverse of each. Okay, here partial fraction is not possible because it is the quadratic whole square. So if you partial fraction, you will get one term and you will again get the same repeated term. So we use convolution here. Okay, and we know the Laplace inverse of s over s square plus 1, it is cos t, and we know the Laplace inverse of 1 over s square plus 1, which is sin t. So if you know the Laplace inverse of fs and gs, then you, by convolution, we can write the Laplace inverse of fs into gs. Okay, so we use this convolution result. Okay, that Laplace inverse of fs gs, if you know the Laplace inverse of fs as ft and gs as gt, then it is equal to 0 to t fu g of t minus u du. Okay, so one of the functions is reversed and shifted, and product with the other function, it's integral from 0 to t. Okay, so one of the inverse is cos t, other is sin t. So I can write sin u into cos of t minus u, or I can write cos u into sin of t minus u, and its integral. Okay, so this left hand side, this third quantity is sin of t. Okay, and this, if I'm using this as f of u, its inverse, so it will be f of u will be cos u, and its Laplace inverse is sin t. So once I shifted it, so it will be sin of t minus u. Okay, now we can solve this integral. It is of the form 2 sin a cos b. If I multiply and divide with 2, so I can write it 2 sin a cos b, and then I can rewrite this. Okay, so multiplying and divide with 2, and also divided with minus t. Okay, and then just integrate this. Okay, so integration is with respect to u, so sin t is like a constant here, so we get u sin t, and for this function we have a cos. Integral of sin is minus cos divided by minus 2, so which becomes plus of half. Okay, and then put the upper limit minus lower limit. Okay, so these limits are limits of u, so this term becomes t sin t for upper limit, and for lower u is 0, so this term is 0, and put u value as t minus u value 0, this term will cancel out, upper limit minus lower limit is 0. Okay, so what we will end up is half of sin t, because this t will cancel out. Okay, and plus 1 by t sin t is already there. Okay, so this is the solution of the differential equation, y t is half sin t plus 1 by t sin t. Now I take one more example. Say solve this second order differential equation, which is non-homogeneous but with constant coefficients. But now the conditions are y0 is equal to 1 and y at t is equal to pi by 2 is minus 1. So conditions are given as a boundary value problem. So one condition is at t0 and other is at t equal to pi by 2. Okay, well, our steps remains the same. Okay, so first step is take the Laplace transform on both sides of this differential equation. So Laplace of left hand side equals Laplace of cos 2t. Use linearity on left hand side, okay, and then use second derivative Laplace this property. So we get this result. Okay, so Laplace of second derivative is s square ys minus sy0 minus y dash 0 and plus 9 times Laplace of y is ys and Laplace of cos 2t is s over s square plus 4. Okay, use whatever initial conditions are given. So we are given y0 is equal to 1, so we substitute it here. Y0 is 1. Y derivative at 0 is not given. Okay, so let us assume that this y dash at 0 be equal to some number, say a. Okay, so use condition and assume this y dash 0 as a. So we put y dash 0 as a here. Okay, combine the ys terms, so s square plus 9 times ys. Y0 is 1, so minus of s minus of a is equal to s over s k plus 4. Okay, now this a is unknown constant, but we can once we have solution we can use this second condition. Okay, t at pi by 2 y is minus 1, we can use this condition to find this constant a once we have the solution yt. Okay, so now solve for ys. So ys, take this s and a to other side and divide with sk plus 9. Okay, so now final step is take Laplace inverse. Okay, so on this denominator product you can use the convolution or you can use partial fraction. Here I am using partial fraction to solve this. So using partial fraction we separated that denominator and so take Laplace inverse on both side of this. Okay, use linearity on the right hand side. Okay, and use that Laplace inverse of ys is yt. And so Laplace inverse of s over sk plus 4 will be cos 2t. Laplace inverse of s over sk plus 9 is cos 3t. And Laplace inverse of 3 over sk plus 9 is sin 3t. Okay, so immediately we have this result where this a is a constant which is to be calculated, and for this we use the condition that y at t equal to pi by 2 is minus 1, so we put t is equal to pi by 2 in this, and left hand side y is minus 1. Okay, so minus 1 equals, when t is pi by 2 is minus 1, so minus 1 by 5. Cos of 3 pi by 2 will be 0, so this term 0, and sin 3 pi by 2 is minus 1, so minus a by 3, so we can solve this to find a as 12 by 5. Okay, put this a back here and we have the solution for the given differential equation. Okay, so we have this solution. So this was one example that boundary conditions are given. So I take one last example to solve the system of differential equations. So instead of one differential equation, you are given a system of differential equations. So there are two equations. D is the derivative with respect to t, and x and y are two dependent variables here. Okay, so dx by dt and dy by dt. dy is dy by dt and d of x is dx by dt. Okay, and given initial condition on x and initial condition on y. Okay, so method still remains the same. Okay, so method says that you take the Laplace transform on both side of the differential equation, and there are two equations, so take Laplace on both side of both equations, so first equation and also the second equation. Okay, so taking Laplace transform on both side of the differential equations, so Laplace transform on left equal to Laplace transform on right, and also on the second equation Laplace transform on left and Laplace transform on right. Okay, use linearity. Okay, so by linearity we can separate the Laplace. Okay, and now we have two dependent variables, so Laplace of x we denote with x of s and Laplace of y we denote with y of s. Okay, and so we know the rule, Laplace of derivative of x will be s x s minus x value at 0, and similarly Laplace of derivative of y will be s y s minus y value at 0. Okay, so Laplace of derivative of x will be sxs minus x0, these two terms, minus 2 times Laplace x, which is minus 2 times xs, plus 3 times Laplace y, and Laplace y is ys, so plus 3ys equal to 0. Similarly 2 times Laplace x is 2xs plus Laplace of derivative of y, so we have this property. Okay, sys minus y0, these two terms for this derivative, and minus Laplace y is minus of ys equal to 0. Okay, and then use the conditions. Okay, so x0 is 8, y0 is 3, so put x0 as 8 here, y0 at 3 here. Okay, and then combine xs terms and ys terms wherever possible. Okay, so use conditions and rewrite these two as system of equations. Okay, so xs combined to s minus 2 times x of s plus 3 times ys, and x0 value is 8, so it goes to other side, equal to 8. Similarly, 2 times xs and these two terms combined, so s minus 1 times y is this, and y0 is 3, so it goes to other side as plus 3. Now we have a system of algebraic equation, so we can solve this to calculate either x function or y function. Okay, so say first we eliminate y from here and calculate x function. Okay, so eliminating y, that means if I multiply first equation with s minus 1 and second with 3 and subtract these two, then ys function will cancel out, and so we have s minus 2 into s minus 1 x, and multiplying second with 3, so we have 6x, so subtracting means minus 6x, and on the right hand side we are multiplying first equation with s minus 1, so 8 times s minus 1, and we are multiplying second equation with 3, so it will become 9, so 8 times s minus 1 minus 9. Okay, so combine these two and calculate x's from here. Okay, so we can combine and then we can calculate x of s as 8s minus 17 over this quantity, which can be written as product of two linear vectors. Use partial fraction. Okay, as we said, we have to take Laplace inverse after this, so we have to use partial fraction and properties. So taking Laplace inverse on both sides. Okay, so immediately by linearity, this is 5 e power minus t, and Laplace inverse of this will be 3 e power 4t. Okay, so immediately we have the result that xt is 5 e power minus t plus 3 e power 4t. Okay. Similarly, we have to find the ys function and then take Laplace inverse to find the yt function. Okay. So again, the previous algebraic equations, which are these two, eliminate xs this time. Okay, and to eliminate xs, we multiply first equation by 2 and second equation by s minus 2, this vector, and subtract, so xs will cancel out. Okay, and we will have equation in ys. Okay, solve this for ys. Okay, so ys can be written as 3s minus 22 over s plus 1 into s minus 4. Resolve this by using partial fraction, and then take Laplace inverse on both sides. Okay, so Laplace inverse of ys will be yt, and Laplace inverse of this by linearity separate it, and then first term will give 5 e power minus t and second will give minus 2 e power 4t. Okay, so this xt function and this yt function together, they form the solution of the original system of differential equations. Okay, so I hope I have done sufficient number of examples now to understand the process. Okay, so in the next lecture I will talk about unit step function and its application on how we can solve or calculate the Laplace transform of piecewise functions. Okay, so its application using Laplace transform, that means how unit step function can help us in calculating the Laplace of piecewise functions. Okay, have a very good day.